So as we move forward in our course outline, remember we've got 3 topics here. We're going to move on to fluid statics, our third pass through. We're looking at this rho GH business, and we're going to formalize it. In other words, I want to ask the question, what happens if rho changes? Formalizing rho GH. It can be shown, in fact there's already videos up on it, that if we sum the forces of pressure and weight acting on a fluid box, little differential element, we can write the following. dP dx is equal to 0. dP dy is equal to 0. dP dz is equal to minus rho g. And that's in a world that looks like x, y, z with gravity acting in the negative z direction. So what are these things? Well, these are little differential equations. They came from the conservation of momentum. Sum of forces has to equal 0 if it's not going to move. And here's how they come in handy. dP dx equals 0. What's that mean? Well, if we had some tank and it had some fluid in it, and we were at some point here, and let's just say that this is our x direction, dP dx equals 0 says that if I move along from here to here, say, the derivative of pressure with respect to x is 0. In other words, pressure doesn't change in the x direction. The only way that dP dx is equal to 0 if you change x is if delta p is 0. Ditto in the y direction. In the z direction, though, we have dP dz is equal to minus rho g. And so what we could do is we could solve this real quick, right? We could write dP on the left, and we can multiply up by rho g, so we get minus rho g dz. And if we integrate both sides, we could write something like P2 minus P1 for the integration constants there is equal to minus rho g times Z2 minus Z1, which, you know, in the past, if we call this Z1 and this Z2, the delta between them we've been calling H. In other words, P2 is equal to P1 plus rho g h. Now, what assumption did I make to do that? I took the rho g and I pulled them out. And so what that means is that this is for a fluid whose density doesn't change, incompressible, and also that gravity hasn't changed. And you're probably asking yourself, well, where would that not be the case? And say for a really tall problem where we're moving way up and the value of the local acceleration due to gravity actually changed. The beauty of writing in this formalized notation here is that we can now realize that this is actually an integrated quantity, and so if rho or g were to change as we go up and down in z, we can handle that. And so that's what the next example is going to be.